Now we're going to look at an example of modeling using what we know about dimensional analysis. This comes from your text, example 5.1. We're asked to look at drag on a copepod, a water crustacean that's about 1 millimeter in diameter. And so we want to know the drag force when it's moving very slowly in fresh water. But that's a really small kind of model to try to deal with. And so in this case, we're actually going to try to make or see if we can make a scale model that's larger work for us. So we can actually fit it inside of our wind tunnel um, and do some meaningful testing on it. And so we're told we're going to use a scale model 100 times larger and test it with glycerin at a velocity of 30 centimeters per second. Then we want to know for similar conditions for velocity and drag on the actual copepod in water, um, assuming that equation 5.2 applies, which is shown right here, and the temperature is 20 degrees C. Um, so uh, to to start out with, we're going to have to first of all figure out what our properties are. Right, so we have fresh water, which is going to be down here. Right, so we're going to have rho W is equal to 998 kilograms per meter cubed. Mu W is going to be 1 times 10 to the minus 3 kilogram per meter second. And then we need to look up the results, the property values in glycerin as well. And that'll be right here, glycerin. Bring it rho G is equal to 1260 kilograms per meters cubed. And mu of that glycerin is going to be, we can look it up, there we go, 1.49 kilogram per meter second. So we can see that while the density of the glycerin is really not that much different than the density of water, the viscosity is actually quite significantly larger. And so in order to actually have an effective model, remember we need to satisfy both geometric and dynamic similarity. We're going to assume that the geometric similarity, this is taken care of by the model. In this case, we're told that we have a scale model, and so we're just going to, I guess, trust the model maker that they've accurately modeled a copepod. I'm not even sure what one of those looks like. And then for dynamic similarity, this is where we're going to match the dimensionless parameters that govern the problem. In this case, this is the Reynolds number. So what this problem is actually asking us to do is to find the velocity from the Reynolds number, and then from the results on the model, we're going to find the drag of the actual copepod in water. Again, by assuming that if we have matched the geometry with our model, and we've matched the Reynolds number with our model, then we can use our model results to translate our measured drag force into the from the model to the real world situation. To start with, we're going to consider that the Reynolds number model is going to be equal to the Reynolds number of the actual copepod, let's say REC. And so rho, the model is in glycerin, times U model times the length of the model over the viscosity of glycerin is going to be equal to rho water times the velocity of the copepod, the thing we're trying to solve for, the length of the copepod over mu water. And we're told that the length C is equal to 1 millimeter. The length of the model is equal to 100 millimeters, or 100 times the length of the actual copepod. And so now we can start plugging in our values and solving for the first part of our problem, which is what is the velocity of the actual copepod. So we're also given that the velocity of the scale model is 30 centimeters per second is equal to 0.3 meters per second. Okay, so the density of glycerin, so this will be 1260 times 0.3 times 100 millimeters. So that's going to be 0.1 meters divided by mu g, and this is 1.49. This is going to be rho water, so 998 times u copepod, the thing we're trying to solve for, times 0.001 over mu water, and that's just 1 times 10 to the minus 3. Right, so we can plug all of this in and solve this. So 1260 times 0.3 times 0.1 divided by 1.49 times 1 e to the minus 3 divided by 998 times 0.001. And from this, we get that UC is equal to 0.0254 with these values meters per second. Your textbook notes puts this into the scale of centimeters per second, so UC is equal to about 2.5 centimeters per second. Great. So that's the velocity solved for. And then we're going to do the same thing with our force. So in this case, the force, measured drag force in the model was 1.3, right? So Fm was equal to 1.3 newtons. And we know that this drag coefficient, Cf, is the thing that is going to be matching between our model and the real world example. Put another way, we basically built the model so that we could measure this coefficient of drag here, because we know that if we matched the Reynolds number and we matched the geometry, meaning if we have dynamic and geometric similarity, then we can use our model results to get an accurate measure of what this CF, or this coefficient of drag is, the coefficient of friction is on this model. And so that's that CF is F over rho V squared L squared, found by dimensional analysis. And so if CF model, CF model is equal to CF of the copepod itself, the real world thing, then that implies that F over rho V squared L squared model is equal to F over rho V squared L squared of that copepod. And so now again, we can just plug in our values, and what we're trying to solve for is this thing, the force, the drag force on the actual copepod in real water. Again, using the results from our model. And so if we plug this in, 1.3 over 1260 kilograms per meter cubed times our velocity. And our velocity was 30 centimeters per second, right on for the model. It's 0.3 meters per second um, squared, and our length of the model was 100 millimeters. So this would be times 0.1 squared, and that's equal to the force on the actual copepod divided by the density of water, 998, times the velocity, that's 0.0254 squared, times the length of the copepod, 0.001 squared. Right? So now we can take this, put this all together, and solve for this. So we're going to have 1.3 times 998 times 0.0254 squared times 0.001 squared divided by 1260 times 0.3 squared times 0.1 squared. And we're going to get something which is really quite small. So our force on the copepod itself is going to work out to 7.38 times 10 to the minus 7 newtons. And so we'll probably express that as FC is 7.4 times 10 to the minus 7 newtons, accounting for significant digits in this problem. And we can see that so using our model results, using our model, we're able to make a prediction for what the drag force on this copepod is here. And this is kind of a nice example because ordinarily when we're considering models, we think of them as being smaller than the thing being studied. We talk about a submarine model as being something that can fit in a lab, and so we want it to be smaller than the actual submarine that we're trying to design. This really highlights another use of modeling, which is for this copepod, it's tiny, right? It's really, really small. It'd be hard to even put such a thing into some kind of a wind or water tunnel. But also the force that you'd be trying to measure on a real copepod is incredibly, incredibly small. So measuring such a thing accurately would be very difficult. So in this case, modeling this copepod and putting it into a material that's very, very viscous, but building a model that's much larger allows us to perform an experiment with a measured force, which is something reasonable, 1.3 newtons, and use that to predict the drag force on the actual organism, which is something that's really, really tiny. So again, just showing the power of dimensional analysis, in this case, modeling, to learn things about how fluids behave.